Welcome, I'm Franchi, and today I'm going to give an overview of our work in detecting disparities in police deployments using dashcam data. I'll adhere to this outline for the presentation. First, I'll begin by setting the stage, discussing the current state of public-facing policing data. Next, I'll provide a brief overview of our process for collecting our data set for police vehicle detection. However, for in-depth technical details, I recommend referring to our paper. The majority of this presentation is dedicated to presenting results on classifier performance and the estimated distribution of NYPD police vehicle deployments. Finally, we'll discuss the implications of these results in relation to the initially outlined stage, and we'll touch upon our plans for future work. Currently, there exists a vast body of literature that leverages large-scale policing data to statistically audit policing in terms of efficiency and equity. However, this literature primarily concentrates on outcomes that occur downstream of police vehicle patterns. In other words, it focuses not on where police go, but on what they do once they arrive. Many algorithms, including pretrial risk assessments and predictive policing algorithms, used in policing and criminal justice, rely on data from outcomes downstream of police deployments, such as arrests and convictions. Consequently, disparities in police deployments can bias the data these algorithms rely on, thereby influencing downstream outcomes. For instance, in To Predict and Serve, Lum and Isaac suggest a feedback loop with predictive policing algorithms where higher deployments result in increased arrest rates at consistent crime levels, which ultimately prompts a recommendation for even greater police deployment. Beyond academia, journalists, activists, and legal practitioners have sustained efforts to quantify disparities in policing. Yet, police deployment data remains largely inaccessible throughout the United States. This data is crucial for several reasons. First, statistical analyses of police deployments have uncovered inefficiencies or inequities, with some areas experiencing disproportionate police deployments. Second, as previously mentioned, disparities in police deployments can result in biases and downstream outcomes such as arrests. Thus, deployment data is vital for auditing police behaviors. In response to this need, we present a novel methodology for monitoring police deployments: the detection of police vehicles and dashcam images taken from public street scenes. We utilize a dataset of approximately 25 million dashcam images gathered across the 5 boroughs of New York City during 2020. From this, we annotated a training dataset of 9,500 images for the presence of police vehicles and trained a YOLO-based deep learning model to identify these vehicles with high accuracy. The initial 1,000 verified true positives for the dataset were obtained through Scale.ai, a platform similar to Amazon Mechanical Turk. We then identified additional positives using a prototype version of the model. Both true and false positives were manually verified and added to the training set. In total, our final training set comprises 4,750 images with police vehicles and 4,750 images without police vehicles. Our data is sourced from Nexar, a company that equips ride-sharing drivers with dashboard cameras to document their rides. While this data spans the 5 boroughs, it does not represent a truly random sample of roadside points in New York City. In response to this, we've made substantial efforts to mitigate dataset biases. First, we adjusted the image distribution to match the population distribution. For instance, to compute the police deployment levels that Asian residents of New York City experience, we rebalanced the original data sample to oversample neighborhoods with larger Asian populations. A more comprehensive mathematical framework illustrating this process can be found in section 4.1 of the paper. Second, we examine disparities in performance across subpopulations and ensure that disparities are minimal across these groups. These results are presented later along with the classifier results. Finally, there are other biases that are unavoidable due to the inherent nature of our dataset. We delve into these in the discussion section. Now onto results. The key metric that underpins our analysis is the probability that residents of a specific group, for example Asian residents, will see a police vehicle when they are on a street in their home neighborhood. This estimator aligns with the roadside nature of the Nexar dataset. Next, let's discuss the classifier itself. Our you-only-look-once powered object detection model is generally well calibrated, and it achieves high performance across the subgroups for which we assess disparities. At our positive classification threshold of 0.77, the model identifies 233,000 images out of nearly 25 million in total as containing a police vehicle. The figure on the right showcases some sample positive detections. As demonstrated in the top left image, the model performs reasonably well even with occluded and small pixel-sized vehicles. Here, we present the aforementioned performance across subgroups as evaluated on the test set. If the difference between the orange and blue dots is smaller than the uncertainty indicated by the length of each line, then there is no statistically significant difference in model performance across the stratification. We examined disparities in police deployments by racial group, zone type, population density, median household income, borough, and neighborhood. The figure here presents an overarching distribution of police deployment rates for the entire city, segmented by neighborhood tabulation areas. Gray areas represent regions with zero population according to census data, including airports, cemeteries, and parks. This figure reveals a striking range in police deployment rates. Gramercy, the neighborhood with the highest police deployment levels, registers at 4.28 times the city average, compared to Arden Heights Rossville at 0.23 times the city average. This is nearly a 20-fold difference. This graph more clearly illustrates the relative deployment levels across neighborhoods, highlighting key observations. Among the top 12 neighborhoods, there's a mixture of two types of areas. Some of the wealthiest parts of New York, for example, Hudson Yards, once described as a billionaire's fantasy city, and some of the most heavily policed, such as Rikers Island, which houses a prison complex. High deployment levels in certain neighborhoods may be influenced by unique neighborhood characteristics. For instance, Gramercy hosts a major police training center located on two busy thoroughfares. Thus, to be more systematic about our analysis, we proceed to investigate correlations with zone and density. As this figure illustrates, commercial zones have much higher deployments, almost 2 times the city average, than residential or manufacturing zones. When we add in density, we get a richer picture. Here, we see that police deployment levels increase dramatically with population density, from 0.65 times the city average in areas in the lowest quartile of density to 1.12 times the city average in areas in the highest quartile of density. Overall, this analysis suggests that one place high police levels are observed is dense commercial regions of downtown Manhattan. Next, we analyzed disparities in police deployments based on race and socioeconomic status, focusing specifically on residential zones to capture where individuals actually live. We observed significant racial disparities. Black and Hispanic residents encounter police deployment rates at 1.08 times the city average, compared to 0.95 for white residents and 0.81 for Asian residents. This represents a 34% discrepancy between the highest and lowest race groups. These findings align with previously observed disparities in New York City, where Black and Hispanic residents were more heavily policed. Upon stratifying by income quartile, we find that police deployments increase as income decreases. Residents of census block groups in the lowest MHI quartile experience police deployments at a rate 1.19 times the city average, while residents in the highest MHI quartile experience police deployments at only 0.91 times the city average. Overall, for the sake of transparency and simplicity, we do report results by stratifying each variable separately. We acknowledge that these disparities are significant in themselves, but multiple causal mechanisms might underlie them. Overall, our analysis speaks to a complex, multifaceted picture of police deployment in New York. We observe considerable spatial inequality in deployment of police vehicles. Residential areas with higher proportions of Black and Hispanic residents or lower income residents experience significantly higher police deployments. Interestingly, dense, affluent commercial areas in downtown Manhattan, such as Hudson Yards, also see high police deployments. This observation aligns with previous research indicating that gentrification correlates with increased police presence. While we employ numerous techniques to minimize bias in our pipeline, effectively providing a template for future computational social science research on non-representative dashcam data, we do acknowledge certain unavoidable limitations. First, despite reweighting the sample so that each census area is weighted proportionally to its population, it's possible that the sample of images within each census area might be biased. For instance, news articles have reported how protests following George Floyd's death blocked traffic throughout the city, inevitably precluding the capture of dashcam images from certain areas. However, the sampling process for the Nexar dataset is somewhat opaque, and the time period analyzed was marked by dramatic changes in social distancing policies and responses to policing. Thus, it would be unwise to assume that no other biases remain. It's also possible that the time period captures trends unique to the COVID-19 pandemic. Secondly, identifiable police vehicles serve only as a partial proxy for all policing activity. They do not account for example, officers on foot or unmarked vehicles. Subway policing, another recent facet of NYPD police activity, is also beyond the reach of dashcam data. Despite these limitations, it's important to note that police vehicles themselves are an insignificant indicator of policing activity. For instance, they conduct traffic stops, which are among the most common ways that Americans interact with the police. And so, our work serves as a call for police deployments to release more comprehensive deployment data. In the past, police have resisted this, arguing that it could compromise public safety. We contend that this claim is questionable for several reasons. Even aggregated deployment data would be highly useful for detecting disparities, as both our work and past research have shown. Moreover, much more granular data on many aspects of policing activity, including stops, searches, arrests, citations, and even shootings, is already publicly accessible. This raises questions about how aggregated deployment data could uniquely jeopardize police operations. The benefits of releasing this data would be substantial, democratizing the ability to audit the police. This project was undertaken using highly specialized resources, and even with these, we encountered unavoidable biases. In essence, our approach is not a viable method for an average citizen to monitor the police. Hence, we renew our call for the release of aggregated deployment data to the public. Our approach underscores the potential of dashcam data for auditing government agencies for efficiency and equity, not just limited to the police, as well as its broader implications for computational social science. We're eager to continue our work using dashcam footage of public street scenes. Given more data, we could replicate this analysis over a more recent and longer period than just a month. Shifting domains, we could perform other audits with dashcam images ranging from street-side garbage detection to accessibility analyses for older adults using public services. And with that, I'd like to thank you. This presentation is part of the 2023 ACM Conference on Fairness, Accountability, and Transparency.